All right, as promised, I would send out a video kind of summarizing the work we've done on quadratic residues. Some of these things we'll prove. At least one of them we won't. I'll just show you the result. But you remember at the end of class on Friday, we've reduced the problem of determining if A is a quadratic residue to these three cases using the fundamental theorem and theorems that got us there. So, -1, in case you can't tell, that's a 1, over P, 2 over P, and then Q over P, where Q and P are odd primes. P is an odd prime through the whole thing here. Q would be another odd prime, and of course, P and Q are different. All right, so to help us with this, Gauss's lemma, a lemma with a wonderful name. Gauss's is our first step. So let's take a look at what it says. Like always, we have an odd prime, and then for each x, from 1 up to this number, p minus 1 over 2, we're going to call it h and think of half, like halfway between 1 and p minus 1 over 2. Let x star be the integer in the interval negative h to h that is congruent to a times x mod p. Okay, because of our condition, x is between 1 and p minus 1, p is prime, then there is an x star. That congruence is solvable. Okay, now we're going to get values between negative h and h. Now it says if exactly n of those values are negative, then a over p is equal to -1 to the n, which means that a is a quadratic residue mod p if n is even, and not if n is odd. Okay, that's what the theorem says. I'm going to prove it. I don't know if it will help you with the work I'm going to ask you to do later to wind our class down, but hopefully you'll at least find it interesting and read through it. And I'm going to prove it differently than the textbook does, just slightly. The proof I'm going to use reduces the solution x star to this interval minus h to h. So they're not really least residues, they're the residues that are the smallest in absolute value. The proof in our textbook just uses least residues, so some things read a little differently, but not that different. So before we prove it, I thought we would do a couple of examples. So let me pull one up here. Here's the first one. If P is 11 and A is 5, so that means H halfway up to 11 is 5. So here's what we're going to do. We're going to write our values out, 1 to H. These are our X values. And then we're going to multiply by 8, so 5 through 25. And now reduce them, mod P. So we're reducing over here, mod 11. And these are the values we get, nice and easy. I'll let you check my arithmetic. You know you need to check it. So make sure. But notice what makes me feel like maybe I didn't make a mistake is that the results we get are the same in absolute value as the values of x. Okay. Not coincidentally. So one more example. Slide this baby up. Now we'll take p equals 17 and a equals 3. Oh, I forgot the punchline up here. So Gauss's lemma says 5 over 11 is -1 to the number of these guys that were negative. Well, we got exactly 2. So -1 squared, and of course that's equal to 1. So 5 is a quadratic residue mod 11. All right, now the case 17. We'll choose randomly, a equals 3. So halfway to 17, we have 8. Here are my x values, the top row. And then we multiply by 3 all the way across. And then we reduce mod 17. So we start off with 3 and 6, and then we'll replace 9 with -8, 12 with -5, and so on. And you can see, once again, we get the values 1 to h in some order, just like we started with the values 1 to h. But some of them are negative. Well, here there are exactly 3 that are negative. So n equals 3. By Gauss's lemma, 3 over 17 is congruent to minus 1 cubed, which is minus 1. So 3 is a quadratic non-residue, mod 17. All right, now let's see if we can prove it. I'm going to pause and get a head start here. To prove Gauss's lemma, first we need to show that the x star values land in the interval minus h to h. And I didn't write it here, but that they are exactly in absolute value, the values 1 through h. That's a pretty straightforward proof. We've done things very much like it before. You assume, 2 of them are congruent to each other, and then you can get a contradiction. So I'm not going to, there's some slight differences because we're dealing with absolute value, but I'm not going to go into the details. We really have provided all of those details in other areas. So we're going to go on to the part that's sort of unique to quadratic residues. So we've got these x stars. They're in the interval minus h to h. They all represent different equivalence classes. And in fact, in absolute value, they are the numbers 1 through h. Then by Fermat, we can say a to the h times the product of the x's. The first few steps are not in Fermat here, but we'll get there. Here we're just doing obvious true things, and hopefully they'll not only be true but helpful. So a to the h times the product of the x's. Remember there are h of them, so h factors here. In fact, the x's are 1 through h. I can push the a's inside since I have h factors on my pi, and I get ax to the h. Well, those are congruent. It's how we chose our x stars. So to the product of the x stars, that's by a proposition back in chapter 2. And then I know that exactly n of the x stars are negative, so I can pull those minus signs off. There they are. And then what's left over are just the x values we started with. Okay? So cancel. I'll do it in red. Those guys are relatively prime to p. The product is, so we can cancel them, and we get that a to the h, which remember is a to the p minus 1 over 2. Is congruent to minus 1 to the n. But we also know by Euler's criterion, a to the p minus 1 over 2 is congruent to a over p. Oh, my a's are ugly. A over p. Yeah, here's another ugly a. And that's mod p. So, right here is the statement we're looking for. And that concludes the proof. All right, as mentioned before, using results we verified on Friday, what we need is the quadratic residue nature of minus 1, 2, and any odd prime. That would give us the nature of the quadratic residue mod p, another odd prime. So here's the case for minus 1. I've pushed it down to the bottom to create a little suspense. So the theorem, I think it's 4.6 in the textbook. It says p is an odd prime, then minus 1 over p is equal, a very simple statement here. In fact, it's easy to prove given the power that we have available. Minus 1 over p is equal to 1 if p is congruent to 1, mod 4, and negative 1 if it's congruent to 3. So a super easy to use assessment. Of course, all odd primes fall in one of these 2 categories, and a nice easy breakdown. If it's in the first category, congruent to 1 mod 4, then minus 1 over p is equal to 1. That is, minus 1 is a quadratic residue. All right, I'm going to prove one of these. I'm going to prove the second one, the case where P is congruent to 3 mod 4. And you can prove the first case in an entirely analogous method. So let's find out. If P is congruent to 3 mod 4, then by the division algorithm, we can write P in the form 4k plus 3 for some integer. Oops, that should be a k. Eraser. Why won't it erase? Okay. Thus, minus 1 to the P minus 1 over 2 equals, plug in the value for P that we have, and reduce it, 4k plus 2 over 2, which reduces to the obviously odd number, 2k plus 1, so it's minus 1. So minus 1 to the P minus 1 over 2 is equal to negative 1. And now we can connect that via Gauss to the quadratic residue by Gauss's lemma. Minus 1 over P is congruent to negative 1, P minus 1 over 2, but we just showed in this case that is minus 1. And so we get minus 1 here just like we needed. We're in this case right here. So that's half of it. You can go to the other case and prove it in an entirely analogous manner. And so let's say similarly, minus 1 over P equals 1. I mean, there's a few little differences, but nothing challenging if P is congruent to 1 mod 4. And so that concludes the theorem. 1 down, 2 to go. For the case A equals 2, we have theorem 4.8. If P bigger than 2 is prime, then 2 over P equals 1 if P is congruent to 1 or 7 mod 8, and it's equal to negative 1 if P is congruent to 3 or 5 mod 8. Again, we can recognize that since P is odd, that those 4 cases, 1, 7, 3, 5, cover all the possibilities. And we get a theorem that's sort of analogous to the one we got for negative 1. It's a little more complicated, having kind of 4 different categories of primes, and evidently to think of them in those 4 categories makes the theorem provable. And while the proof is similar to the proof for minus 1, it actually is quite a bit more detail oriented. And so I'm not going to actually prove it here. It's proved in the textbook, so if you're curious, take a look at it. But we'll focus on rather using it, and let's just practice a little bit. Let's take something like 5. Sorry, getting ahead of myself. 217. So 17 is 2 times 8 plus 1. It's congruent to 1 mod 8, and so therefore 2 is a quadratic residue. So 2 over 59. So 56 is a multiple of 8. So 59 is congruent to 3 mod 8. So 2 is not a quadratic residue, mod 59. Let's try something like this. 1871. So you might be saying, wait a minute, we're talking about 2, not 18. Yeah, but we know some things. So 18 is 2 times 9. And by a theorem from Friday, 2 over 71 equals 9, times 9 over 71. We prove that's true. We know that 9 is always a quadratic residue, at least if p is bigger than 9. So we have something times 1, and 71 is congruent to 7 mod 8, 72 being a multiple. So 18 is a quadratic residue. 17, etc. And maybe I'll put some of these on the work that you have yet to do. Which leaves one thing, and that is the law of quadratic reciprocity. Let me set it up, and I'll be right back.